Hi, I'm Dave Robinson. I work at Stack Overflow, and I'm going to be talking about gganimate, my package for animation within the grammar of graphics. So how many people here use ggplot2? Awesome. How many people feel they're familiar with the term the grammar of graphics? Right. So a good number of you. It's interesting because I sometimes do get people wondering, what is the grammar of graphics? When I talk, and I do talk about it a lot, I think it's a really important part of understanding visualization is what exactly ggplot2 is doing. So the grammar of graphics was originally developed by Leland Wilkinson and then popularized and somewhat modified by Hadley Wickham, who spoke earlier today, to create the ggplot2 package, which is really one implementation of that. The way that I like to explain the grammar of graphics is is based on Garrick Rolliman's really great cheat sheet on the, can I get like a mobile microphone a second? Because I like to look back at the screen when I talk. Does anyone have a mobile microphone, like the one we had for the, no one? All right, I'll wait on it, yeah. What it talks about is the relationship between data and eventual visualization. So you start with your data, which is in one form of one observation per row, and you move on to represent the relationships between that and the size and the visual dimensions of the plot, such as the x and y axes, the size, and the color. And this is a really good representation. And I like to use usually actually Hans Rosling's talk from the TED Talk on the best stats I've ever seen with a Gapminder dataset. So we've actually seen this dataset 2 times already today from Hadley Wickham and from Eduardo, talking about, recognize this graph, where we see the income per person versus the life expectancy for countries around the world. So you've already seen it, and you might notice we have particular dimensions of this plot. And if you go to gapminder.org and you take a look at this, it's actually an interactive, really cool interactive plot where you can see the, you can choose the x-axis. Here I used per capita income. You choose the y-axis. Here I chose life expectancy. You can choose what to put on the aesthetic of color and on the aesthetic of size. So this is a point where you get complete control of the grammar of graphics. And this relates back to the tool of ggplot2. The way we would control it in ggplot2 is with a call something like this. We would take our data. The data would look like we get one row for each country, a variable for the life expectancy, and a variable for the GDP per capita. And we would see that's the data, and then we show its relationships of the x-axis going to the GDP per capita, and the y-axis going to the life expectancy. So that AES call is about representing relationships between our data and the plot. We could choose to add another aesthetic. Here we already have X and Y up, but we would choose to add size and say the population variable gets mapped to size, which then affects the size of the particular points on the plot. We could choose to add another one. We've got X, Y, size, and color. We map continent to color with a 4th line in the aesthetic mapping, and we get to say what each of these variables in our data end up being represented in our visual representation. So this is a visualization conference, so you might want to make the plot a bit bit better than this. But you can see that we throw in a few more lines, add labels to the x and y axes, and once we've done that, it's really pretty, we're getting pretty close to representing the Gapminder plot. We can see this, the story that this tells, the story of a relationship between income and life expectancy, and that positive relationship between them. We can see how you have the Americas and Europe ahead, Africa behind. They have different color scales in these, but we've really represented it. But you've all seen in the 2 talks so far today, you've all seen this isn't all there is to the Gapminder dataset. There's time. You can see that as it goes on, we get, Spanish flu, and then we head up through the 30s. And in general, really here, you start to see a good increase of World War II. And follow the bouncing red ball, because that's China going up in both income and then life expectancy. And you see it progressing. Africa's still staying behind, but growing with the rest of them. If you watch Africa in the 90s, you saw a bit of a decrease. And what you're seeing is this trend over time as a 5th dimension in the plot. And that's one that isn't represented within the grammar of graphics, because our data actually, it didn't look like what I was showing before. The full Gapminder data set looks like this. It represents one row for each combination of a year and a country. You have 1 year for 1952, 57, 62, and each one of these gets one frame in the plot. And that means in current animation solutions, you usually have to do something like this. So the animation package by Yihui Shi is a really terrific package generally for creating any kind of animation, but it requires you to work like this, to say, I want to make one plot for each year in my data set, or each frame in my data set. You get a for y in unique. You might do a filtering step after that. You might use a split function or one of the pure functions, but you put it together and you end up getting, you get one plot for 1952, one plot for 1957, 62, 67. You're creating all of these plots. That is one solution. But what I feel is really important about this is the recognition that just as you have an X and a Y aesthetic, and you add in the size aesthetic and color, there's a fifth aesthetic here that ggplot2 can't map to, and that's frame, seen from 1952 through 1977 and beyond. So that's where gganimate comes in. So the gganimate package, which I released earlier this year, takes a data set and maps an aesthetic explicitly to frame. So here I say take the year variable and use that to use the frame of the animation to represent year. After that, you give it to a gganimate call, and that is what creates the animation. So if you put this code into based on the Gapminder data set, you get this animation right out. And here you can actually see what is coming up on the same information that the Gapminder website showed. Actually, did anyone make it to Hadley Wickham's talk at the visualization meetup yesterday? It was neat. He actually showed this, this same animation. It was showing how we have X, Y, size, color, and time. So gganimate works by treating frame or time as another visual aesthetic to be represented in a ggplot2 call. As I mentioned, there are other approaches to animation, most of which tend to involve creating one plot for each frame. So what advantages does gganimate, treating it as an aesthetic, have over them? First, mostly that it gets to take advantage of understanding the ggplot object structure and use that to create an efficient plot. So one of the big ways is, this is a very recent development, it can now build by layer. So it doesn't actually build a separate plot for every single time point. Instead, it builds the background once, then creates one transparent plot for 1952, throws that on, one for 57, throws that on, one for 62 throws that on, and using image magic, this ends up to combine them into an animation. This ends up being a lot more efficient to create a GIF, an animation that's very compact and fast to create. Beyond that, you keep scales consistent, which is a real danger when you create animations with ggplot2, where it assigns its own legends and decides its own scales. If we created one plot for 52, it would look like this. One plot for 57, like this. One plot for 2007, skipping ahead, looks like this. And watching it as an animation, those look pretty good. Okay, you can understand it, until you compare them side by side. And you notice that, in fact, they have different y-axis scales and different size scales. So you would have had to create an animation, you would have had to decide those scales in advance for your data. And that's what gganimate automates for you, creating a scale on the full data and then playing it through. So that's one way that it makes it a lot easier. Another is that it's really set up to work with some modern tools in RStudio and the R ecosystem, such as working with RStudio notebooks. Here I wrote up a little chunk that has just the Gapminder animation I showed, and we play it, and oh, there it goes. So you can play it as part of your notebook. You can have it pop up as in a snippet on the side. Ramnath has created an animation widget that actually lets you browse through it with buttons. We've come up with ways that can make this, these animations really easy to create and more powerful. One of the really cool features that you can choose here is that it's very easy to say, I want to animate this layer and not this layer. Here, for example, I did 2 geom point layers on our Gapminder dataset, one in black, one on top of it in red, and the red one was animated. That's great for when you want to highlight points rather than just show them moving. Here we see all the points at once, and we choose to highlight each year one at a time. And you create a lot more complicated things that way by building an entire ggplot and deciding which parts to animate. Another is that you can choose to make a layer cumulative with a cumulative equals true aesthetic. And cumulative plots can be really useful when you want to see something, you want to see a full picture, but you want to see it build. So here's a version where we chose to make it a geom path. Oh. There it goes. We chose to make it a geom path, and there it goes. It animates through, and you see those geom paths climbing over time and slowly building. So we're seeing it still keeps all the old layers, although frames, but then it builds on top of them. If you take a look at Africa, you can see several of the countries that Hadley was mentioning in his earlier talk that dropped back down during the 90s. I want to give a shout out to a really great package called Tweenar that works with, as an input to gganimate for interpolation. So in this step, what we did is we took the data set and then we said, we want to split it by year and use tweening to get points between them. We then end up with a new data set that looks something like this. We only had 1952, 1957, 1962, and that led to a really jerky plot. It wasn't smooth motion. But by using the Tweenar package, we can create one for each intermediate year, which then gets its own frame aesthetic. And when you feed this into gganimate, as I do below, you're able to get continuous motion. We didn't add any extra data. This still had from 1952, 57, 62. But the Tweenar package let us interpolate linear motion between them. So watch it bounce and go and follow through. And that does look a lot like what the gapminder.org website looks like. The Tweenar package does allow for alternative smoothers. Here's a cubic in and out smoother that actually lets it speed up and pause for a second on each of them. And there's really cool things you can do if you start using this package. Thomas Peterson has on the README for the package, he has this animation where he made using Tweenar and gganimate, where he has one ball and has it move around the screen, bounce and wobble, and change colors along the way. And this is all done with shockingly little code, because all he did was create a few data frames about where he wanted them to end up, and then use Tweenar to connect them and gganimate to plot the results. He's made a lot of really cool examples. I'll show one more later in the talk. And yeah, this is where I want to show a couple examples of what people have created using the gganimate package since its inception. One of the first ones I created, since I set it up in February, I had this data frame that I put into a gganimate, and some people might recognize this input data as polar equations, specifically a cardioid. So I put that in because it was in February, so I was able to make this for my wife. So that was a good start. More recently, just a couple weeks ago, a journalist came up with a win probability over time for Clinton based on various projections. So this was using cumulative equals true and following over time, up and then down. And you see 538, generally the most pessimistic, goes way up in October, goes down, and the rest is history. And one of the interesting things to me about this graph is that all the information that you saw in the animation is up here right now. You could have simply shown a line graph. But by seeing it build, there is a visceral connection to understanding what it's like to go up, down, that this actually communicates. Someone else, I really like Male Salmon, came up with one that was data surfing. So she had an air quality data set and she just added one, I think it's GG emoji or whatever it is, of a surfer following along it. And that I kind of got a kick out of. And there's a lot of things you can do with making your plots cumulative. It is literally an extra 20 characters of code to take any GG plot you have and make it cumulative. But you can get a lot more complicated. I really liked this post from Jacob Kunst about visualizing chess data with ggplot2. So this downloaded a large amount of tournament chess data, move by move, and then used R to process it and ggplot2 to visualize it to show, for example, where one bishop went over the course of a game, what the most common moves were. So I was able to take this and adapt it to an animation. So here we see the first 40 moves of tournament chess. And you see the knight got out immediately, the rook took longer, and still the rook ends up staying on the same side of the board that it stays. So watch that knight really, knight really hops out right away. Knight, bishop, queen, rook, the latecomer to the game. You can see this and tell this story of something happening over time with an animation. Population pyramids were mentioned earlier as a really good data visualization, and a lot of them want to be animated. This in particular is a demographic period showing the aging of India. And here you can see both males and females. So here you can see population structure and let it change. I really like this one from James Curley, which took some NBA data and again, surprisingly few lines of code turned into an actual story of what areas of the court do NBA players cover. And watch that orange ball circle, because that's the basketball, and does he score in this? I don't even, nah. Oh, and he passes it. So you can see you can actually build these stories and see these things really easily once you've tied in your data to the grammar of graphics. Here's one that really can't be done in any way other than animation, and that's Conway's Game of Life, where there are particular rules for each item of the cellular automaton. So while this was created using a for loop, in the original code, it was then turned into a data frame related to time, and then we can see how this dynamic system progresses. This one's one of my favorites. This is created by the same person who created Tweener as network interactions over time. There's a chunk of code here, but I'm really impressed still with what can be done with relatively little. This is, there it goes. This is showing human interactions within a social network over the course of one conference. I think that had something to do with infection data, but it's really a way you can see over the course of this time period where things start and how they progress. It's a combination of the gganimate package and the ggraph package for visualizing networks. Both of them are ways of tying in something to ggplot2 that hadn't been done before. I've shown a lot of data visualizations with this, but I really liked Michael's talk in the last section about not just telling stories, not just analyzing data, but showing concepts. And I think animation has a special role to play in communicating concepts. Here, for example, is a trigonometry description where you see here's a circle, it's traveling around, and you can see the related sine and cosine curves that happen from the lengths of those particular x and y segments over time. What I like about this as an animation is this represents a relationship between every point on a circle and every point in those graphs. That's a relationship you can't show with a visual geometric object. You can't draw a line between every pairing. By letting them happen at the same time, you let the viewer understand these relationships. I also like the example of bootstrapping. Bootstrapping is an iterative process, and that means you do it a whole bunch of times, and it's hard to visualize it for just one. So here I took a data set using So here I took a data set using the modelar package, which is one of Wickham's newest packages for taking data and perform particular kinds of operations useful for machine learning and modeling in a tidy framework. And that introduces the bootstrap function. And with a few more steps, we're able to take these bootstrapped samples, put them into a data frame, and then animate them. And in this case, what I'd show is every step here is one bootstrap sampling. Every point is how often that point was sampled. So you can see that in this bootstrapping, some points will be skipped out on one animation, and as a result, they don't affect the resulting best fit line. And some others will be oversampled. Some will appear 3, 4, 5 times, and each of those times it'll change where that line gets placed. And by doing this many times, you get to show how bootstrapping works in terms of creating a linear relationship for each, build them all together into a confidence interval, a measure of uncertainty. One thing this does is gives us a bit more space to play with in our graph. For example, we can still use faceting on this. So I take Anscombe's quartet, which is a common way of representing particular mistakes that people can make in linear regression. We tidy it, do the same bootstrapping on it, and facet by each item of the quartet. And here we see how different items within the quartet respond to bootstrapping. And we can see that some of them will really get this particular curve, but that a case like where there's a single outlier, you end up seeing it really represents, that's an entirely different confidence interval than you would have come up with through parametric methods. And this you can communicate because you can show every item of the iteration and show them building. There's just a geom point and a geom smooth, with the smooth being cumulative. There's another I'm fond of, I won't show a code for it, is if you have some processes that aren't necessarily iterative, but they are about a moving window. Moving windows can be quite tough to represent because they're all overlapping, and showing them all at the same time is going to be really challenging to parse out. But you can show them sliding with an animation. So the code for this is up on my Twitter, and this is locally weighted regression, where at every point you choose one x, and you just take the region around it and weigh that area upwards when you're choosing the line. Build the centers of each line, and you can see that regression, that best fit line riding along the curve of our data. You can also see that as you change the bandwidth from 0.25, taking only a quarter of the points into account, to 1, where we're generally taking all the points into account, how the resulting curve ends up changing. That's because it takes, at every point, a wider range of the data into consideration. As one more sliding window method, we have kernel density estimation. Kernel density estimation is similar, but for a one-dimensional data where we can see our points scattered up at the top, and we choose to move a sliding window along them, and the total density that sliding window covers is what gets tracked. So I really like this as a communication because the equations behind kernel density estimation can be really opaque. But by seeing that what you're doing is you're sliding over it and seeing, how many points is this gray area covering, you're able to build it up piece by piece. You can also see here the change to the bandwidth between 0.25, where it only considers the points right around it, so you get that little point up at the top, at the start of the 0.25 bandwidth, and the ones that are much wider, and the data ends up looking much more like two normal distributions. So that's kernel density estimation, and that concludes the examples I wanted to show. But I want to talk about that really is what animation is useful for. It's useful for, we can take another dimension in already high-dimensional data, like the Gapminder dataset. We can take a sense of progression to a time series, take something that would fit just as a line, but let you animate along it and give you this visceral understanding of going up then down. You can take an implied iterative dimension in an algorithm, such as bootstrapping, where you have one frame for each bootstrap sample, or kernel density estimation, where you have one frame for each x, and this implied step gets turned into time. and you can use it to show a hard-to-communicate relationship, like between one point on the unit circle and the resulting points in the sine and cosine curve. So sometimes I think interactive plots are really popular now, and I really love interactive plots. They're such a great way to communicate information, especially to scientists or to yourself or people that want to explore something. But there's something that animation really is special for, and that's for telling a story. There it is. Let's see. That's for taking something where you want to communicate a single story from the start to finish, and it's really easy to communicate it and really easy to share it. It's really great to be able to create an animation and then tweet it or blog it, and immediately people who see it will get this full relationship that you're representing. And I think that's one thing that I think, Shiny and Plotly and a lot of tools for interactive graphics are really essential for exploring data. This is really a really great way of telling a story at the end of it. Thank you. So I'm at drob on Twitter. You can find my blog at varianceexplained.org, and you can install the gganimate package. Try it out. Any questions?
Hey Dave, thanks. Good talk. I noticed that in your animation where you were showing how the transparent foreground is rendered against a static, sorry, an animated foreground is animated against a static background, the title, oh thank you, the title moved with the plot data. I'm wondering what the relationship of that title was to the plot data.
Yeah, good question. Here, by default, gganimate uses the title as a way of communicating where in the animation you are. It's not the only way, and it can be turned off with one argument. Some of these I chose to leave the title off. But if you want to show, here you generally want to show year. And if you take a look at, even if you take a look before, let's see, actually that one, let's see. Well, here you can actually see we had a different title for each. Wow, I'm really taking my time going through these. What you see is you do have 1957, 52, 62 of these going up through there, and that is because, by default it chooses a title based on each frame. That can be turned off or it can be appended to. An alternative is to have a geom text that would pop up somewhere on the screen and use a frame equals argument within that, which would let you put any title you wanted somewhere else on the page. That's awesome. I think I haven't thought about integrating it. I think where each of them has a useful point is whether you're exploring your data or communicating the results. And communicating the results, I found animations have a really important role in communicating a specific message to a large number of people who might not know much about your data. One of the things I've discovered is if you send Shiny apps to people that maybe aren't statistically experienced, they might not think of the right things to go for, the right sliders to move, and this lets you guide it at least in one stage. It's different if you were communicating it to a scientist. The other advantage is it's easier to share. So an animation file is something like a 500 kilobyte file that can be shared in a tweet or on Facebook, and something that can be immediately shared. You don't have to go to a link and then try out some things, and it's fast to load. So there is, I think, that step of, I completely agree that this could have been represented this could be represented, we think, oh, we have a Shiny app and one slider for this. But there is a way that this is much easier to communicate, and I think it fits a really important part of the communication in data science ecosystem.
Have you considered any type of automatic way to provide a cue as to what part of the animation you're in? Because I know if I see this immediately, I don't necessarily know how long I'm going to wait to get to the end.
Yeah, that's a really good question. You could always build a progress bar as a geom that, say, builds up. As an automated way, I think Ramnath had something about that in the HTML widget he was building around gganimate. I don't remember how that ended up. And I think it's an interesting idea. I think if it's a video, you can always see how long the video is. And I should have mentioned gganimate does write out to GIFs, but also to MP4 and a few other formats that you then can see how long it is. But yeah, and the others you could say, yeah.
Sorry to interrupt.
Yeah.
I think just on this idea in general, it would be interesting to, what if the title went across the top of the
Yeah, totally.
as time goes on or something?
Yeah, I could totally imagine that. And for the title going across the graph, you probably have to just stick spaces in or something like that. But yeah.
Hi. How about real-time process monitoring, looking back, say 20 minutes, maybe 4 parameters, 4 separate graphs simultaneously?
Oh, interesting. I never thought of it using that way. The process for building an animation can take a second or it can take minutes, depending on how many frames you have and how intricate each of them are. That's the first thing I think and it is one fixed animation. It does create a file. I don't think it's particularly well suited to say, I think if you wanted to make an animation that was live updated and always showed recent history, you probably want to find a way to pull that off in Shiny or a JavaScript tool. But if you want to create one every 20 minutes, it's definitely possible depending on the complexity in an automated process, depending on how visually intense and how many frames you had in each animation and how long it would take, therefore how long it would take to render.
So historically, gganimate relies on image magic to splice the frames together if you want to export it. Is that right? Is it
Yes.
with a new layer functionality? Does that remove that requirement?
That fits into image magic. It's with the when you use convert, you can have the option to set one background for all the layers. I'm actively working right now on making that requirement easier. The magic package is one good tool that allows a C++ backend to image manipulation. I haven't gotten it to work with that particular structure yet. It's something I'm intently interested in because that kernel density estimation ended up being a few megabytes large, which it really is more than you'd want to use to share in most media. So I am really interested in what can make it faster and also what makes it an easier process to install. As I said, the magic package just has a C++ package that compiles. It would take at least a little bit of tinkering to get it to work with some of the things we do. Yeah. We're done?